Hello, everybody. I excuse my voice, but it's better than 3 days ago. I want to talk with you about the influence of enforced social distances on GEM and evacuation times. This is a work together with the East Bavarian Technical University. Katharina Schwab was the student who did the major work for her bachelor thesis, and together with Simtego. I want to give you some objectives of this work, an overview of the model data, and an example of evaluation of this data. And then, of course, some results of the global evaluation. How did we come across to this? Well, Thunderhead Engineering introduced social distance behavior to Pathfinder in August 2020 as a method to address pandemic safety in evacuation simulations. This was brand new, and nobody knew how the results of those simulations would be. So we thought we would like to know more about these forced social distances in contrast to the personal distances, especially with different agents that keep different social distances from relatively small, from 1 meter, to relatively large, say 3 meters. So what was the results that we were looking on? It was the effect on the flow and exit times and GEM times. And what could these results be used for? Well, first of all, waiting times and length of queues, but especially what we got later on, a lot of work asked for was changing times, especially for examples in high schools and universities or cinemas in pandemic situations. So what was the implementation in Pathfinder? What we all knew in the years was the personal distance. Well, this is a desired distance one occupant will try to maintain with others in a queue or a GEM. And it's a gap distance. So it's between the occupants' shapes. It's a shoulder-to-shoulder distance, and it's not strictly enforced. And in the manual, you can read it should be maximum 1 meter. Whereas the social distance is a constant value or a distribution of values. It's center to center, so it's not shoulder to shoulder measured. It's enforced, and it should be larger than 1 meter. Movement groups do not perform social distance with other members of their own group or of the same group by default. But, of course, it is possible. So we did a variation. The variation we have in this study is a lot larger than what I will present now to you. I have chosen 3 rooms, so a room of 250 square meters with 2 doors, which is due to German legislation. Then we copied this room and just made out of 2 times 250 square meters of 500 square meters with 4 doors, and we copied it again to make an exact mirroring with 1,000 square meters and a lot more doors that our German legislation would give us for such a big room. Why did we copy these rooms? We wanted to have no other side effects. So we came with the thought that if we would copy this room twice and make it in this position always larger, then the results should be more or less the same. So we filled up these rooms with groups without any social distance. And also with groups with a constant social distance of 1.5 meters, 2 meters, and 3 meters, and with uniform social distances from 1 to 2 meters or 1 to 3 meters. And then, of course, we had to find out, for all these variations, what is the maximum load of numbers of people, of agents, for these rooms. And then we used groups with stochastic parameters. So occupant speed, we used stochastic parameters between 0.5 to 2.0 meters per second. And for shoulder width, we have in Germany a DIN, so a norm that says the shoulder width in our group is between 0.4 to 0.55 meters. No, not really. It's a bit, the numbers are a bit differentiating from this because these measured shoulder widths are naked. And we thought like the agents we will use, they will have clothes on, so we added 2 centimeters to it. And then we made 4 different groups saying change these parameters, so have a constant occupation speed and a variation of shoulder widths or otherwise around or both constant or both variation. So altogether, we had more than 10,000 runs. And this is just an image of this 250 square meter rooms. And of course, we have a different load of agent for these rooms because of the different parameters sets that we put in. So this is a 500 square meter room and just another time copied the 1,000 square meter room. So what is the results that you can get out? The first is the social distance. You can show with this spacing discs. You have to decide full size or half size. And then you can see just visually the overlap of your discs. So if you want to print it full size, then you get a good overlap of the disk, but you can't say anymore is for every agent this social distance in the right order that I want it to be or not. Even with the half size, you can't say it, because if you have different sizes, then they might overlap still. Therefore, we have the other parameters like social linkage. It gives you the number of agents within a radius R of an occupant, or social usage, which is the same stuff, but not for a person or an agent, for a spot on the ground. But for this social usage, it takes occupant movement groups not into account. And then we have the analysis approach, which means over what period of time are how many occupants closer than a given distance. First of all, for the results, we printed out such diagrams. And of course, like we had heard yesterday, and it was like a huge amount of data. It happened what should not happen. Here I have another chart into my file than what I told on the right side it would be. So this is an example for 1,000 square meter rooms and 459 occupants with a social distance between 1 and 2 meters. But it's just an example, so it doesn't really matter. It's just to show you how we treated the data. So here you can see only one run. Every point on that slide shows you the result for one agent. So blue is exit times, green is jam times, red is jam time continues. And of course here you can even visually see the maximum for the exit time, which is at this example 1.67 minutes. But this is only a run, and if you compare it to 10,000 runs, this is not suitable. So for our Monte Carlo distribution, every scenario we did repeat with 500 different input parameter. So we needed a way to address the results. So we used this form, so you can see here the distribution of max gem time continuous for 500 sample run. And you can see on the left side there is a minimum of 0.25 minutes to a maximum. And in the middle you can see here the mean value and the standard deviation. This we used for our stochastic runs. And then we printed it out as histograms. So for the 500 runs, we decided to make this histograms to make it a bit more seen and clearly what is the distribution of our of the different results of these runs. So with this, you can see very clearly where the bullet point is in your results. But overall, it's still so many different results that you have to print next to each other, and it's not good to get a feeling of your results. So we printed all together in this diagram. So you can see here occupants per square meters, then the social distance on the left-hand side, and the color show the exit time. This is not a false, this white rectangle on the top. It means just you're not able to put in an occupant density of two occupants per square meters, and on the same hand have a social distance of 3 meters between your occupants. Therefore, it is white on the right top. Here for the color, you can see the exit times. And therefore, you can see, okay, with these lines printed in, it should make it a bit more clear here to see that is a line of 120 seconds, and here you can see the line of 90 seconds. Altogether, all runs to make it a bit more clear. And what we found out was, pretty much simple, saying the bigger the social distance in the same room, the smaller is the density and exit times. And by fortune, when we printed the same one for max total gem time, we found out the same. The bigger the social distance, the smaller the density, then the smaller the max total gem time. The same for max gem time continuous. But when we looked at the videos, there was something that you can't see in these results. It was the feeling, but they are still slower. So how could we express this in numbers, what you could see, but what you can't see in the diagram? So we decided to make a normalized time for all those times, so a normalized time by the number of occupants. So by dividing for example, the maximum exit time by the number of people for those runs, we found out that the normalized exit time per occupant with a social distance of example 1.5 meter is 2.3 times bigger than without a social distance. And if the social distance is even bigger, so let's say 3 meters, then this time is also increasing. So for a social time, for a social distance of 3 meters, we have a 4.5 times larger normalized exit times than without social distance. So you can say the normal gem times per agent is increasing with an increasing increasing social distance. The conclusion of our work. We did a lot of simulation. This is just for the 3 very simple rooms. We used it, but also for the university rooms and corridors, which we finally found out brought the same results. The evacuation simulations with social distances in Pathfinder showed that density and social distances have an influence on exit times and social and jam times. The bigger the social distance is in the same room with the maximum possible number of occupants, the smaller are exit times and jam times. The normalized exit times are increasing with an increasing social distance by an enormous factor, how I think, from more than 2 to more than 4. And for jam times, from around 2 to about 3. But there is no significant difference between a constant social distance to a uniform distribution for the same density. And we could also not find significant difference if you use grouping. So the behavior then is about the same like if you have a uniform distribution, or the results at least. Well, thank you for your attention. Many thanks for me to Katharina Schwab, which did really a huge work here as a bachelor thesis, and to Simtego, and especially thanks today to my grandmother, because my grandmother, she has her 79th birthday today, and so it's good to be here, and yeah, I hope to see her in good health soon. Thank you.
Thank you for presentation. You're talking about social distance. I was wondering if you have tried something reverse like social attraction, and I am wondering if we are not making a small mistake or maybe a big mistake considering that in crowds, everybody is a single agent. Because I travel with my wife, with my kids, and in all the crowds I can see in real life, I see more groups of people socially attracted by each other than finally individual people. So I was wondering if there would be some research you are doing, or maybe somebody else, on this impact of having groups who wants to be away from each other also.
We did this in the study that came just after this, when we used these results for the filling and refilling of university rooms. There we grouped the half of the occupants in groups to 2 to 4 persons. So because for students it's not normal to be like 10, 15 persons, so we grouped them like a family together, 2 to 4 persons, and about half of the population. And we found out that the results were about, if you have a normal distribution in the social distance. So there's no, we couldn't find a special effect if you have those small groups and about 50% of your occupants as a group. There you can't see a big difference to it. Because then other agents, solo agents, will fill in the gaps. So it's not, you can't see it in the times.
Hi, thanks for the talk and happy birthday to your grandma.
Thank you.
You showed one of the interesting results. It says that when you increase the social distancing, the density decreases and the exit time decreases too. It was in a slide before.
In a slide before.
I think this one here, maybe.
Exit time.
Yeah.
Yeah.
So I would expect if the social distancing increases, that the density decreases. So did you have a scenario where you change the social distancing, you increase it, for example, but then have the same density in the room still? And then compare the exit times and see if it goes up or down. Because if the density decreases, it's obviously the exit time will decrease either too. So
yes,
so,
yes, of course. Well, yeah, for bigger social distances, of course, you have a decrease in density, of course. But we had also fillings with a uniform density, with a uniform social distancing, so that the density was bigger than without, or than with the same, when every agent has the same social density. And for the bigger the social density in the room, so you can make a Durchschnitt to it.
Mean value, average.
Yeah, an average, thank you. An average to it. Then you can say the smaller exit times. So
it's somehow counterintuitive. I didn't make the simulation, but just think about it. If I have many people that have to keep some social distancing, they should take more time to exit the room than people who are packed together.
yeah, but it's a phenomenon that it's other agents will fill in these gaps, and those agents, basically, if you have no social distance, they would stay maybe and wait just in front of the door. If you have no social distance, so it's not a matter for the exit time at this, for this special case.
Okay, thank you.
Just following on from the last point, I think, I guess what you could do is do a comparison between a relatively low population density that was just the starting position. So there's 1.5 persons per metre squared or whatever it is, and then the same initial density with social distancing, and do a comparison to see whether it's the social distancing or the low density that has the effect. Do you know what I mean? Because one is just an initial condition that produces, that controls the number of people in the room, whereas the others are dynamic, right? It evolves over time. So I'm just wondering, that might be an interesting thing, because then the difference then is because of the social distancing as opposed to the number of people in the room.
Yeah. We did this in a later study when we did it for the university rooms. Yeah, it will be more information in the paper. I'm sorry that I can't answer this straight away, but there's more information in the paper.
Sorry for the second question. Do you think it's, of course it's counterintuitive, but don't you think it's the same phenomenon like when you put an obstacle just in front of a door, then you have a better flow, and then with social distance, when people try to keep apart from each other, there is less conflict, and then better flow?
Definitely, yeah.
Just a small question followed by Steve and I. I'm curious, like you say, the exit time decrease with the social distance increase, but is it like from the social distance difference, or is it from the total number at the start of the room? Since if there is less people in the room, and it is common to know that the exit time we will have a shorter exit time. So which factor contributes to the shortened time of the exit?
If you compare it to the maximum usage of the room, then of course it's the density that makes the biggest point to it. For the first question here, it was the question to compare it to the maximum usage of the room for this special case. And for the second question, so what is if I don't use the maximum usage of the room, if I compare it to the same number of person, this was not a question of this special study. We did it later on with the university rooms. I can't tell you now straight away, but it was more or less the same results. But you can read it in the paper. There will be more information given in the paper.
Thank you. I'm looking forward to that paper.
Yeah, and just a note on that, those usually follow the conference by about 2 weeks or so. We get everything organized and published and give access, so you should have access to all of that information. Thank you very much.